Welcome to the solution overview for LeetCode problem number 1025, Divisor game. In this video, we'll explore the problem, discuss potential approaches, and break down the solution step by step. Let's dive in. In this problem, Alice and Bob are playing a game where they take turns, with Alice always starting first. The game begins with a number n written on the chalkboard. On each turn, the current player must choose a positive integer x such that x is a divisor of n and 1 equals x less than n. Once the player selects x, they subtract it from n, effectively replacing n with nx. The game continues until one of the players is unable to make a move. If a player cannot find a valid x on their turn, they lose the game. Importantly, both players are assumed to play optimally, meaning they will make the best possible moves to maximize their chances of winning. The goal is to determine whether Alice will win the game, and the output will be true if Alice wins, or false if she loses. Let's go through an example to better understand how the game works. Suppose the initial value of n is 2. Alice starts first and chooses x equals 1 because 1 is a divisor of 2 and it satisfies the condition 1 equals x less than n. After subtracting 1 from 2, the new value of n becomes 1. Now it's Bob's turn, but there are no divisors of 1 that meet the condition for a valid move. Since Bob cannot make a move, he loses the game, and Alice wins. Therefore, the output for this input is true. Now consider another example where n is 3. Alice starts and selects x equals 1 because 1 is a divisor of 3 and it satisfies the condition 1 equals x less than n. After subtracting 1 from 3, the new value of n becomes 2. It's Bob's turn, and he chooses x equals 1 since that's a valid divisor of 2. Subtracting 1 from 2 results in n equals 1. At this point, it's Alice's turn again, but there are no valid moves for her because there are no divisors of 1 that satisfy the condition. Since Alice cannot play, she loses, and Bob wins. Thus, the output for this input is false. Let's analyze one more example where n starts at 4. Alice begins by choosing x equals 1, which is a valid divisor of 4. After subtracting 1 from 4, the new value of n is 3. Now it's Bob's turn, and he selects x equals 1, which is a valid divisor of 3. Subtracting 1 from 3 results in n equals 2. It's Alice's turn again, and she chooses x equals 1, subtracting it from 2 to make n equals 1. At this stage, Bob is unable to make a valid move because there are no divisors of 1 that meet the conditions. Since Bob cannot play, he loses, and Alice wins. Therefore, the output for this input is true. The problem also comes with a few constraints and edge cases. First, the value of n will always be between 1 and 10,000, inclusively. For edge cases, if n equals 1, Alice cannot make a valid move on her first turn and loses immediately, so the result is false. For large values of n, such as the maximum constraint of 10,000, the solution needs to remain efficient. Additionally, there's a key observation regarding the parity of n. If n is even, Alice always has a winning strategy. On the other hand, if n is odd, Bob always wins, assuming both players follow optimal strategies. Understanding these patterns can help us reason about the solution more effectively. To tackle the divisor game, we first consider the brute force simulation approach. The intuition here is straightforward. For any given number n, if there's at least one move that forces the opponent into a losing position, the current player wins. To implement this, we iterate over all possible divisors of n, those integers x where 1 equals x less than n and n% x equals 0. For each valid x, we subtract it from n and recursively determine whether the opponent loses with the new value of nx. If we find any move that guarantees a win, we return true for the current player, otherwise, false. However, this approach is computationally expensive. Due to recursion, the time complexity grows exponentially as we explore multiple divisors at every step, making it infeasible for large values of n. Additionally, it consumes linear space in the recursion stack. While simple to conceptualize, this method highlights the need for a more efficient strategy. A more refined approach involves dynamic programming, which builds on the insights from the brute force method. Instead of exploring all moves recursively, we iteratively compute the game's outcome for every number from 1 to n. We define a Boolean array dp, where dp, I, indicates whether the starting player can win with the number I. The base case is clear: if n equals 1, Alice has no valid moves, so dp 1 equals false. For each number I greater than 1, we check all its divisors x where 1 equals x less than I, and if there's any divisor that leaves the opponent in a losing position, meaning dp I x equals false, we set dp I equals true. Otherwise, Alice cannot force a win, so dp I equals false. While this approach significantly reduces the computational cost compared to brute force, its time complexity is still quadratic because we iterate over divisors for each number, making it less suitable for very large n. Now, we need an even more efficient solution. The most elegant and efficient approach leverages mathematical analysis. The key observation here is that the winner can be solely determined by the parity of n. If n is even, Alice can always force Bob into an odd position by subtracting an odd divisor, such as 1. Conversely, if n is odd, every valid move results in an even number for Bob, allowing him to maintain this pattern and ensure Alice always faces an odd number. This simple parity-based reasoning reduces the problem to a constant time check: return true if n is even and false if it's odd. This approach is not only the fastest, with 1 time and space complexity, but also the most elegant. By focusing on the mathematical structure of the game, we bypass the need for simulation or intermediate storage entirely. This realization about parity was that aha moment that transformed the problem from a computational challenge into a straightforward logical deduction. Compared to brute force and dynamic programming, this method is clearly superior, especially for large inputs, making it the ideal strategy for solving the divisor game. The divisor game challenges us to determine if the first player has a guaranteed winning strategy given a number, n, and specific game rules. The game begins with n, and on each turn, a player picks a divisor x such that 1 equals x less than n and subtracts x from n. A player loses if they cannot make a valid move. To solve this, we can start with a brute force simulation. First, we define the base case: if n equals 1, there are no valid divisors, so the current player automatically loses. This means for n equals 1, the result is false. Next, we build a recursive function to simulate the game for n greater than 1. For each valid divisor x, we subtract x from n and recursively check if the opponent is forced into a losing position. If we find any such x where the opponent loses, the current player wins. Otherwise, they lose. The goal is to systematically explore all possibilities to determine the winner. If we break this down further, the key insight is that the current player wins if there exists a divisor x such that the opponent, in their turn, is forced into a losing position. In other words, if the recursive call for n x returns false, the current player has a winning strategy. On the other hand, if no such x exists, the current player loses. The recursion ends either when n equals 1, which is our base case, or when all divisors have been checked. To implement this approach, we define a helper function, canWinN, that returns true if the current player can win for a given n. Inside this function, we iterate through all divisors of n and use recursive calls to evaluate the opponent's position for each possible move. This recursive structure naturally leads to repeated calculations for the same values of n, making memoization a critical optimization. By storing results for previously computed values of n, we can avoid redundant work and significantly improve efficiency. To further optimize the solution, we need to focus on how we enumerate the divisors of n. Instead of checking every number up to n, we can iterate only up to the square root of n. For each number that divides n evenly, both the divisor and its complement can be added to the list. This reduces the number of iterations while ensuring we find all divisors. Additionally, the problem exhibits an optimal substructure. If the opponent is forced into a losing position for any valid move, the current player can guarantee a win by making that move. To support these optimizations, we use two key data structures. First, a memoization table, such as a dictionary or list, stores the results of canWinN for previously computed values of n, avoiding redundant calculations. Second, we use a temporary list to store divisors during each recursive call. Combining these optimizations leads to a more efficient solution with reduced time complexity. The divisor enumeration process can be made even more efficient. Instead of iterating through all numbers from 1 to n, we iterate only up to the square root of n and compute divisors in pairs. This saves computation time while ensuring we capture all divisors. Now, let's look at the pseudocode for the algorithm. We start by defining a memoization dictionary to store results of can when n. The base case is straightforward. If n equals 1, the result is false because the player loses. For other values of n, if the result is already cached in the memo, we return it immediately. Otherwise, we iterate through all possible divisors x of n. For each valid x, we check if the opponent loses when the game state is updated to nx. If the opponent loses, the current player wins, and we store true in the memo before returning it. If no winning move exists, we store false in the memo and return it. This recursive process ensures all possibilities are explored while leveraging memoization to avoid redundant calculations. To illustrate the algorithm, consider an example where n equals 10. We call canWin 10 and evaluate all possible divisors of 10 to determine if the first player has a winning strategy. The function uses memoization to cache intermediate results, making future calls more efficient. In terms of complexity, without memoization, the time complexity would be exponential due to repeated recursive calls. With memoization, however, the time complexity is reduced to O and *d, where d is the average number of divisors per number. The space complexity is O n for the memoization table, and the recursion stack also requires O n space in the worst case. This combination of memoization and efficient divisor enumeration ensures that the solution is both correct and optimized for larger values of n. This solution leverages a mathematical observation about the problem. The game's rules state that each player must subtract a divisor of the current number from it, and the player unable to make a move loses. After analyzing the game's state transitions, we find that the outcome depends entirely on whether the starting number n is even or odd. If n is even, the first player has a winning strategy. They can always pick a divisor x equals 1, leaving the opponent with an odd number. From there, the second player will always face an odd number, and since subtracting a divisor of an odd number always results in an even number, the first player will keep forcing the second player into an odd number. Eventually, the second player will lose when they reach 1. Conversely, if n is odd, the first player cannot win. Any divisor of an odd number is odd, and subtracting an odd divisor from an odd number results in an even number. This means the second player will always start their turn with an even number and can use the same strategy described earlier to force the first player into losing. The implementation is a direct translation of this logic. The function checks if n is even using the modulo operator, n%2 equals 0, and returns true if so, indicating the first player can win. Otherwise, it returns false, indicating the first player will lose. The solution runs in constant time O(1), since it consists of a single mathematical operation and a return statement. This is the Java implementation of LeetCode problem number 1025, Divisor Game. The logic mirrors the Python solution, determining the winner based on whether the input number n is even or odd. In Java, we use the same modulo operation for this purpose, and the class structure is standard for LeetCode submissions. The method divisor game is implemented as a public Boolean function, matching the return type expected in Java. In the divisor game, we have two players, Alice and Bob, who take turns playing. The starting number is n, and on each turn, the current player selects a positive divisor x of n, with the condition that x cannot equal n. The player then subtracts x from n, and the new value of n determines the next turn. The player who cannot make a move loses the game. The key to solving this problem lies in observing that the winner is determined solely by whether n is even or odd. If n is even, Alice, as the first player, can always win. If n is odd, Bob, the second player, will always win. This insight allows us to solve the problem efficiently by simply checking the parity of n. If n is even, we return true for Alice's win, otherwise, we return false. Let's explore this with an example where n equals 2. Since n is even, Alice starts the game. On her turn, Alice can choose x equals 1, because 1 is a divisor of 2. After making her move, the value of n becomes 2, 1 equals 1. Now it is Bob's turn, and he is left with n equals 1. However, Bob cannot make a move because the only divisor of 1 is 1 itself, which is not allowed by the rules. Since Bob cannot play, he loses the game, and Alice wins. This confirms that when n is even, Alice can always win the game. The output in this case is true. Now consider the case where n equals 3. Here, n is odd, and Alice starts the game. On her turn, Alice can only choose x equals 1, as 1 is the only divisor of 3 other than 3 itself. After her move, the value of n becomes 3, 1 equals 2. Now it's Bob's turn, and he has n equals 2, which is even. Bob can choose x equals 1, reducing n to 2, 1 equals 1. On Alice's next turn, she is faced with n equals 1, and like before, there are no valid moves for her since the only divisor of 1 is not allowed. Alice loses the game, and Bob wins. Thus, the output here is false. Let's take another example with n equals 4. In the initial state, n is even, so Alice begins. On her turn, Alice has multiple choices for x. She could pick x equals 1 or x equals 2, as both are divisors of 4. Let's say Alice chooses x equals 1. After her move, the value of n becomes 4, 1 equals 3. Now Bob takes his turn with n equals 3, an odd number. The only valid move for Bob is to pick x equals 1, which reduces n to 3, 1 equals 2. At this point, the game continues with Alice having n equals 2, which is even. With n equals 2 on Alice's turn, she can choose x equals 1, reducing n to 2, 1 equals 1. Now it's Bob's turn, and he is left with n equals 1. However, Bob cannot make a move because there are no valid divisors of 1 that meet the rules. As a result, Bob loses, and Alice wins. The output for this example is true. From these examples, we can make a final observation: when n is even, Alice can always ensure that Bob plays with an odd number, guaranteeing her victory. On the other hand, if n is odd, Alice's first move will leave Bob with an even number, allowing him to win by applying the same strategy. The solution simply checks whether n is even using the condition n%2 equals 0, and returns true if it is, or false otherwise. In this problem, the time complexity of the solution is constant, or O(1). This is because the algorithm only involves determining whether the input number, n, is even or odd. To do this, it uses the modulus operator, n%2 equals 0, which checks divisibility by 2. The modulus operation is a simple arithmetic calculation that executes in constant time, regardless of the size of n. Similarly, the comparison operation, which checks if the result of the modulus operation equals 0, also operates in O(1) time. Since these are the only operations performed, the time complexity remains constant in all cases, whether best, average, or worst. The algorithm doesn't scale with n, making it extremely efficient and predictable in terms of runtime. Now, looking at the space complexity, the solution is also O(1) or constant. This is because the algorithm does not use any additional memory beyond the input parameter and the result it computes. It doesn't create or rely on data structures like arrays or lists, and it doesn't need to store intermediate results. The input variable, n, is simply passed as a parameter to the function, and the computation happens directly without requiring extra memory allocation. The output, whether true or false, is returned immediately, with no additional storage requirements beyond the function's execution stack. This lack of dependence on the size of n ensures that the space complexity remains constant. When we compare this optimized solution to a more naive approach, the efficiency becomes even more apparent. A brute force method might involve simulating the game by iteratively finding and selecting divisors of n, reducing n step by step. This approach would involve considerable overhead because finding all divisors of n can take n time for a single step. Moreover, since the game would require multiple rounds, the time complexity would grow, potentially exceeding n, depending on how many iterations are needed. In contrast, the optimized solution relies on a mathematical observation: if n is even, the first player always wins because they can leave their opponent with an odd number. Conversely, if n is odd, the first player loses because all divisors of an odd number are odd, ensuring the second player can always force an even number back. This insight eliminates the need for iterative calculations entirely, reducing the problem to a single modulus check, which achieves constant time and space complexity. Finally, let's solidify this understanding with a mathematical view of the big O complexities. For time complexity, the algorithm performs only two operations: a modulus calculation and a comparison. Both of these are constant time operations, which means the total time complexity is O(1). For space complexity, no additional memory is used apart from the input parameter, n, and the result, which is either true or false. The solution doesn't require auxiliary data structures or iterative memory allocation, so the space complexity is also O(1). What makes this solution optimal is that it avoids iterative or recursive approaches entirely, solving the problem in constant time and space. This level of efficiency is possible due to the mathematical insight that the game's outcome depends solely on whether n is even or odd, allowing us to bypass more computationally expensive methods. When tackling the divisor game, there are a few common mistakes to watch out for. First, not handling edge cases for small values of n like 1 or 2 can lead to incorrect results. These edge cases often serve as the base cases for recursive or dynamic solutions, so it's crucial to define them explicitly. Another issue is infinite recursion or stack overflow, which can arise in brute force approaches if you don't properly terminate the recursion. Always ensure the recursion stops once n is reduced to 1 or another base case. Additionally, overlooking memoization in recursive solutions can be problematic. Without it, you may repeatedly calculate the same states, causing exponential time complexity. Using a cache to store already computed results can significantly optimize your solution. Finally, there's a common misconception where divisors are assumed to include n itself. Remember, valid divisors in this game are strictly less than n, so make sure your implementation respects this rule. Another frequent error is incorrectly determining the winner. The logic here hinges on forcing the opponent into a losing state, so any misinterpretation of recursive calls can lead to the wrong result. It's essential to carefully track which player has the advantage at every step. From an interview perspective, this problem offers a great opportunity to demonstrate your understanding of game theory fundamentals and recursive problem solving. Interviewers may ask you to explain your thought process, so be clear and concise. Highlight the optimal substructure of the problem by showing how it can be broken into smaller subproblems, which is key for dynamic programming approaches. You should also discuss the trade-offs between recursive and iterative implementations. For instance, while recursion with memoization is effective, it can lead to stack overflow in some cases, whereas an iterative approach avoids this issue. Finally, always be ready to analyze time complexity. For brute force methods, this might be exponential, but with optimization, solutions often achieve complexity around O and *sqrt n, especially when using divisor-based calculations. In terms of related problems, there are several that build on similar concepts. LeetCode 292, the NIM game, is another game theory problem that involves determining the winner using logic similar to the divisor game. LeetCode 877, the Stone game, focuses more on making optimal moves in a two-player setup. Of course, LeetCode 1025, the divisor game itself, directly tests your understanding of these principles. For a more complex variation, LeetCode 1140, Stone Game 2, expands on game theory with a larger state space to navigate. When it comes to alternative approaches, dynamic programming is a powerful tool. It avoids recursion stack issues and provides clarity through a state table, though it may use more memory. Typically, its time complexity is O and *sqrt n, because it involves divisor enumeration for each state. On the other hand, mathematical insights can sometimes offer an even simpler solution. For example, in the divisor game, the outcome can be determined by whether n is odd or even, reducing the time complexity to O(1) in such cases. Greedy algorithms also present an alternative approach, especially in variations of the game. These focus on choosing the largest divisor at each step to potentially achieve faster convergence. While this heuristic is not always optimal, it can work well in certain game scenarios. By understanding these different strategies and being aware of common pitfalls, you'll be better equipped to solve problems involving game theory. This depth of knowledge not only helps you tackle coding challenges effectively but also prepares you for interviews where reasoning through such scenarios is a key part of the evaluation process. Thanks for tuning in. We covered the brute force simulation approach to solving the divisor game and highlighted key considerations like scalability and game theory concepts. Don't forget to subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!